with that one last time we did it. All right. I'm panicking. I did hit record. Okay. All right. Let's. Let's go ahead and jump in here. Good question about the can we have the reaction happening twice, basically? If we add sodium amide to acetylene, could we deprotonate the acetylene twice? Not really, because every polyprotic acid has the same feature where the second proton is a lot harder to pull off than the first. Like in the case of sulfuric acid, H2SO4 has a pKa that's like -7.
Yeah.
Versus HSO4 -1 still has a proton to give up, but the pKa for that is like 2. So it's like a factor of 10 to the 9 difference in terms of equilibrium constants. So like, I can't say no, it won't happen, but it's probably not gonna be a measurable amount.
Like a billion times less.
Right, exactly.
And then with that too, if we, because normally you would do these two reactions separately, so you would do the treatment with sodium
Amide,
right? And sodium amide, and then you would take the product out of that and then treat it with the substrate.
exactly.
Or the
Well, and really, it's so the first step. I'm just gonna throw this one up there as a good example. You don't really need to take it out and purify it. You can do these. You just need to do it sequentially. It doesn't mean necessarily that you have to purify between steps 1 and 2. We will a lot of times, but in this case, it will probably do steps 1 and 2. We call it a one-pot synthesis, where you do it all together. Do this first and give it that amide chance to deprotonate it. If you threw it all in there at the same time, this is going to act as a nucleophile on that. But if you do this first and then just give it the time to reach equilibrium, then you'll wind up with it being sodium acetylide. And the ammonia might still stick around, but for the most part, ammonia is at a pretty high vapor pressure, so it'll basically leave as a gas. And then you can add your methylamide.
So if you do the one pot, you might get like a trace amount of molecules where it has a methyl attached to either side, but it's not going to be
exactly.
Okay.
And that's one of the reasons why we do recrystallizations. So much if you've got a whole bunch of trace products of impurities and one major product, a recrystallization is a really good way to purify it, because if you have a small amount of a ton of different things, they will all have a solubility in your, if you choose your recrystallization solvent well, they'll all have a high enough solubility that in ice water they will stay fully dissolved. And so you can actually purify any number of things basically from a crude product by doing the recrystallization, because everything, as long as its solubility is greater than the amount of it that you have, it'll all pretty much stay dissolved when you do your recrystallization, which is why it's such a good purification technique. Is you're not removing one thing at a time, you're removing everything. As long as you're under 5% yield with it, you can remove a ton of stuff at the same time. Yeah, you lose some of your product too, but the product you get back is, I can't say immeasurably more pure, because it is literally measurable, but it's way more pure. Orders of magnitude more pure. But because that also does take away some of our product, we don't want to do a ton of recrystallizations. Recrystallizations don't usually work well if we have a minor product that is like 40% yield. If we have like a 40-60 mixture, then a recrystallization is not going to work as well, because that 40% still is probably going to be soluble enough that you're gonna wind up with some of that precipitating back out when you cool it back down. But it works really well when you've got a bunch of stuff in single digit yields. Along with your major product. Why are alkynes less common than alkenes? I mean, generally speaking, because they're less stable. And you have to do 2 dehydrogenations, and the 2 dehydrogenation reactions. If you're gonna do 2 elimination reactions on a big long molecule, usually it's gonna be 2 alkenes that are conjugated because you get that extra resonance stability. You don't get any resonance stability with alkynes. So it just basically because of the stability, you just don't see alkynes in nature that often.
Could you theorize a sort of life that uses alkynes, much like Star Trek uses silicone?
I mean, you certainly could, and you can, they're really useful in biochemistry studies because they don't occur that much in nature, but they're not toxic. And so we actually use them to do basically to link things together. If you can chemically model or modify one protein to have an azide group. So if we had some protein and then we just add this molecule or this functional group called an azide to it. And then if we wanted to add to say track where that protein goes in the cell, you can actually chemically modify green fluorescent protein to have an alkyne off the end. And alkynes are more reactive, but they're not so reactive that it's going to react with anything. This preferentially will basically react with the amide, and you wind up making this sort of aromatic linkage that looks like the protein to the other side. And the nice thing about that is green fluorescent protein glows when you shine UV on it. So you literally can just use a microscope and a UV lamp to track where in the cell, what organelles does a specific protein move to, by using the fact that this is not a common functional group in life. So, and the nice thing about it not being a common functional group means that our cells don't have any enzymes designed around breaking it down. If we tried to use something that was really common in nature, our cells' protective, enzymes have ways of basically just chopping up foreign DNA before it becomes expressed very much, right? And so by using something that doesn't occur in nature, we actually get an easier way of doing that. I mean, and in the levels that we're talking about, if you flood anything with a synthetic molecule, it can wind up causing issues. But it's usually more that it just gets in the way, not so much that it's actually toxic. Like, you could probably drink gasoline without it hurting your body too much. It would be more of a physical nuisance or danger than it would be an actual chemical. It's not your body's going to process it and it's going to be a poison. It's more like it would coat your digestive system and not let you digest other things, get in the way, gum up the works, so to speak. Probably not the stomach lining, but maybe the intestines. It might interact with the cell membranes, in mucous membranes, and in your intestines. Your stomach is pretty acidic, and so it's actually not going to absorb very much non-polar stuff in the stomach directly. That mostly happens once you get the intestines, I think. But I don't teach A&P, so don't quote me on that.
My favorite example of dose-dependent poison versus medicine is atropine, because it's a weird one where it has a therapeutic dose. Too much is bad and too little is bad. Like too little can cause bradycardia. It's like, so it's just weird.
Exactly.
It's a treat.
Exactly.
Yeah.
There's reason that's been a saying going back to the Middle Ages, to alchemy times. The poison is in the dose.
Yeah.
Because it's all about how much you have. Of pretty much every medication or anything you can eat or drink for that matter. Question going through the answer, to get the answer here. First step is we deprotonate one of these carbons, doesn't matter which one, because they're identical, right? And then we let it react with methyl iodide, so we're gonna start by making. And add a methyl group here. The CH3, but I'm just gonna try to keep the nomenclature consistent so we can see where we're doing everything. Then we're gonna deprotonate the other side. And add an ethyl group, so we'll get ethyl group. Alkyne. Methyl group. And then the last step is a dissolving metal reaction. Which partially hydrogenates an alkyne, and that leaves us cis or trans? Trans. So we'll get CH3, CH2, there's our ethyl group. Here's our alkene that we're gonna be left with, and in the trans position, we'll put the other methyl group. So we'll get 1, 2, 3, 4, 5, so it's gonna be trans 2-pentene. Would be the name for it.
You said like trans or anti-American, so or you landed on.
E. Not anti specific to talking about the mechanism of the addition reactions. We don't use it to describe the molecules. So E is or trans would both work. I'm not, partial credit for anti, because I know what you're trying to say.
I put both of them on there just because I know we managed.
When in doubt. All right, any other questions about the quiz?
I got some deodorant over the weekend and it has hydrofluorocarbon 152A, which it says I wanted to see what your thoughts are. Sounds terrible.
Let me.
I didn't use it.
What was it in? Oh, okay. Most fluorocarbons get used because they're really low amounts of intermolecular forces, so they're not sticky. Like Teflon is basically a polymer made of fully fluorinated alkanes. So a lot of times it'll be some sort of an anti-friction or anti-chafing. If it's for an antiperspirant, that's probably not an antiperspirant on its own.
First ingredient,
butane, not an antiperspirant. So most antiperspirants are aluminum based.
Yeah.
Because the aluminum actually interferes with your sweat glands and actually stops you from sweating. That's why it's an antiperspirant, not a deodorant. Deodorants basically just cover up the smell. But in both cases, you might have something like hydrofluorocarbon 152A. Hydrofluorocarbon 152A. Probably it's like a base that gets used as a it's a propellant. So it's just what actually sprays the antiperspirant out. And the butane, yeah. So it's an alternative to chlorofluorocarbons, and it doesn't break down the same way in the upper atmosphere to cause problems with the ozone layer. So it's not as good as a refrigerant and a propellant as a CFC, but it doesn't have the ecological concerns. That's what it looks like. It's basically 1,1-difluoroethane. So, but a lot of times in the chemical industry, they'll patent them under certain names that aren't the IUPAC names.
Yeah.
So they patented as hydrofluorocarbon 152A got patent approved to be used as a refrigerant or something like that, and that gives them the way the intellectual property works with most chemistry is it gives them like a 7-year head start, where because they were the group that designed and workshopped and patented a particular molecule for a specific use. You can't patent like 1,1-difluoroethane itself because it's just a molecule and anybody can make that, but it's what they actually patent is the use of that molecule as a propellant gets patented.
Yeah.
But a lot of times the patented names aren't the IUPAC names.
Right.
Even though the patent itself will have the IUPAC name in it.
Yeah, I didn't know how to quite break that down, just of what we've learned. And I don't know.
Yeah.
It's always something scary.
Yeah, I mean, Wikipedia is generally a pretty balanced use because it'll provide links. It'll say, you know, if there's a controversial use or there's been claims of, you know, vaccines causing autism, Wikipedia will give it time to say this was made, claim was made, and here's peer-reviewed articles that talk about that. So I like Wikipedia as a science source to just kind of get up to date on, you know, obviously if you want more details, going directly to the peer-reviewed sources is great, but it's a great place to start because it'll give you the right links to look for.
Yeah.
Also, like, I think about like who's gonna be the person writing the article, like, it's not gonna be some troll, like.
Right.
Writing about, you know.
Yeah, it's not a if it's, as long as it's not a politicized issue, then you don't wind up, and the other thing that you can do is on Wikipedia is you can check what the edit history has been, and if you see that there's been a whole bunch of back and forth where somebody makes a correction and somebody undoes the correction and then they make the correct, like, if you can see the Wikipedia edit wars going on, then okay, like take that section with a grain of salt.
It's like a Reddit page.
A little bit, yeah. You said who's going in and messing with the chemical properties. I actually had it back in the mid 2000s. When Wikipedia was new and all the teachers were still like, don't use Wikipedia. It's you know, it's worthless. You can't trust it. I had a math teacher who gave us a take-home problem that involved using the radius of the moon for something. And he specifically told us, don't use Wikipedia. And then he went in there, son of a bitch, went in there and he changed the values on Wikipedia by one significant figure. Just enough so that if you used that, you would still get an answer that was close to the right answer, and anybody who actually needed to use the radius of the moon for something wouldn't probably notice the difference. But he knew to be looking for it. It was off by like, you know, 1%. He changed it, but it was enough. He said, I know 3 of you use Wikipedia, and I can tell you exactly why. So you do get that. That's the kind of person that messes with the articles on the science. And it was right, and he went back and he fixed it after our test was due.
I bet it is.
All right, let's keep going here. Got some more practice. Predict the products with 1 pentine reacts with each of the following reagents. So just a quick review of alkyne reactions. Without drawing it out, I'll give you each a chance to draw these products out, but just to recap. Sulfuric acid with mercury, what reaction is that going to give us? Markov-Makov hydration, right? Which in alkyne then turns into a carbonyl. All these 2 equivalent ones, same reaction happening twice, right? If it doesn't specify the stoichiometry, here in this case, assume it's 2, that there's 2 because we can't stop it halfway. Then we've got anti-Markov-Makov hydration. One possible reaction, so you should be left with an alkene from this one. And then our dissolving metal reaction. Oh, sorry, you're right. That is deprotonate and then add a methyl group. Always double check how many carbons you're drawing with these alkynes. It's easier than this one. So for A, We're gonna put on more substituted carbon, and it's gonna rearrange to make it carbonyl, so we're gonna get. We haven't learned nomenclature for ketones yet. It's like maybe
own.
yeah, just like alcohols. So it'd be 2-pentanone. So that would be A, B,
Is there an alkene in that structure, then would be and Tina?
pentene, yeah, so
Gotcha.
if we had that, then then you do need to put the numbers in the middle of the name to indicate which number goes to the first functional group. So we could say this was. If that's 2, this is carbon 3, so we could say 3. 10, 10, 2 ohm. And just be, over exaggerate the pronunciation so that it doesn't get mistaken for an alkene. But yeah, anytime we have more than one functional group, we wind up doing the same thing. Now, alkenes, that happens relatively often. So B is gonna give us the same thing except for their carbonyl on carbon 1. We're gonna get the aldehyde. 1, 2, 3. We again, just like with ketones, with aldehydes, you instead of adding OL to the end, you add AL to the end. So it'd be pentanal instead of pentanol. Pentanol will be the alcohol, pentanal is the aldehyde.
And this one's the anti-Markovnikov.
And this one's anti-Markovnikov, we put the oxygen on the less substituted carbon. Two equivalents of HBr. Markovnikov or anti? Markovnikov, so it'd be 2,2-dibromomentane. If we did it with a little bit of peroxide, any peroxide, then we would get the anti-Markovnikov version. One equivalent of HCl is going to do the same thing, so only once. So we're going to leave an alkene. Still Markovnikov, so we're going to put chlorine on the more substituted carbon. So we should be left with this molecule. We're doing 2 equivalents of Br2. Was complaining about how that door was the noisy part of the room to my wife, and she's like, "Yeah, they didn't think it through." And then I thought about it, where else could we put a door in this room? Like I guess we could put it on the hallway over there.
Just make it kind of tedious.
But it would make it kind of tedious, and they didn't want to put it right across the hall from the entrance to the lab, because if a class is getting out here and a class is getting out there at the same time, they didn't want people running into each other. It create a lot of congestion. So there just really isn't a better spot for it, other than, but we could put up maybe some more sound insulation or something over there.
Put a spread trap or the ceiling with a rope ladder.
Rope ladder? I don't know. You must be in better shape than me, but because rope ladders are a lot harder than I remember them as a kid. And if you haven't done this recently, try going on monkey bars as an adult. Monkey bars as an adult are awful. Yeah. Things to enjoy about getting older. All right, so 2 equivalents of Br2 in carbon tetrachloride. Carbon tetrachloride is just a really common completely non-polar solvent. It's not going to react as non-polar, aprotic. So that's just serving as our solvent here. So we're gonna do, we don't really have to worry about Markov or anti for this one because it's
You're gonna
providing
have
the same
four,
thing to both
yeah.
sides. So we're going to, first step would be add a bromine and a bromine and leave a double bond. If you do it twice, we get the 1122 tetrabromopentane. You, generally speaking, this version of this reaction, you don't need to worry too much about the stereochemistry. It'll still happen anti both times. But you don't need to worry about it too much because you're starting from something linear. So, and you're not going to see alkynes in a ring structure very often where you would need to worry about that. We take this molecule, deprotonate it, add a methyl group, which adding one more carbon to the other side, and still leaves the double bond. Or sorry, the triple bond. Right, so we would get 2 hexane. Doing that. And then last but not least, we hydrogenate it over platinum. We can assume we're doing complete hydrogenation. We just wind up with pentane. If we do this reaction over a poison catalyst, not the rainy
Cis
nickel,
version of the.
you would get the cis version of the alkene. I'm blanking on what the name of that Lindler's catalyst. I keep trying to say rainy nickel and it's not that. Lindler catalyst gives us the cis product, and the dissolving metal reaction gives us the trans product.
That was a weird one, that was like the palladium and some other random crap in there.
No, it was sodium metal in liquid ammonia.
Oh, that's the others, okay.
No, sorry, this
That's like-
is the
isn't that
dissolving
the
metal.
Birch? Isn't it called Birch reaction as well, or is that more?
That's a different thing,
That's for like aromatics, right?
right? And
Yeah.
the birch reduction will hydrogenate. I have to look at that one. I know that one, we do touch on that one, and that's important both in pharmaceuticals and in meth production. It involves, I'm trying to think of what the actual reaction is. I think it might reduce a carbonyl to an alcohol and an sp3 carbon. I think might be what it does. It is a reduction for sure, but I don't think it's a straight hydrogenation of an alkene like that. Then again, I'm not exactly current on my meth making.
Good disclaimer.
Synthesis. So. All right, so questions about alkynes? Yeah, so you would get just pentane. Pentane, get the alkane. You're actually fully hydrogenated.
If it's 2H.
It should be two, it should say 2 equivalents of H2O.
Yeah.
Because as it's written, you would actually get, if it's just 1 equivalent of H2, but with platinum, you will get half of this, half a mole of this winds up as the pentane and the other half doesn't react. Because once it starts reacting, it'll finish reacting rather than go do it halfway. So this should say 2 equivalents to be fully correct. Or 1 equivalent over the Lindler catalyst. 1 equivalent over the Lindler catalyst would give us the cis alkene. Not that we could actually tell the difference in this case anyway, because it's not in the middle. We wouldn't actually get a cis or a trans product here. We did that right, because we would just be. So there is no cis or trans. One carbon has the same 2 things attached.
And for F, you said that still at the time, just another message we've got to do this for.
Yes, we'd add another one, so we get the 2 hexane. And so alkynes really aren't that much to add. You know, it gives us, we had, the biggest thing we added was now we have a way to add carbons to a carbon structure by using this procedure. But the rest of it is just a little small variations on reactions we've already talked about. All right, so, and this is week 4. I think that this next chapter is the last one that's on the midterm. It's a little bit different. We're getting into free radicals. But let me. There we go. Let me pull up the syllabus schedule just so we can be sure and all on the same page, because week 4 means midterms is sneaking up on us, right?
Have all kind of questions before the midterm.
Yes. Yeah, this having me teach over at the high school too really throws me off, because yesterday was the first day of their second semester. So it's week 4 for you guys. You're a third of the way through this class, but I'm just starting a brand new class with them. So I'm like, just doing syllabus stuff with them really throws off my sense of timing when it comes to figuring out what's going on. I think in general, so it is in week 6. It made more sense based on the material to do alkenes, alkynes, and free radicals, breaks it up and then the midterm breaks it up nicely. If we had pushed it back a week, then we'd have to include another chapter on the midterm that doesn't fit as cleanly with the same stuff. So it's actually in everybody's best interest to do it week 6, I think. I'm not always tied to exam days, but I always try to make it fit the material, so that we're not kind of breaking up a subject that naturally goes together. No, I know. I like to take suggestions seriously though, because I'm always looking for ways to improve the class, right? Make it work for the people we have this year. Yeah, so that'll be 2 weeks from Thursday, and we're going to talk about synthesis in there as well. So basically we're going to add free radical reactions and then do a couple lectures just on, now let's use all these new tools we just added. How do we actually solve some synthesis problems? And so, yeah, the exam is February 13th, the Thursday, and we'll have exam review that week as well. All right. Yeah. Yep, just like usual. Cool. Then let's talk about free radical reactions. We've kind of hinted at this before. We've used maybe even the same figure before to talk about how bonds break. Most of the reactions we deal with are heterolytic bonds breaking, especially anytime you've got a difference in electronegativity between your 2 atoms. Those bonds will tend to break when the electrons will go with the more electronegative atom. So you don't usually see homolytic bond cleavage unless X and Y are the same strength of electronegativity, basically, or other very specific cases. But that's why peroxides tend to be seen a lot in free radical reactions, because it's you want to end up with 2 really electronegative elements, but they're both equally strong when you have a peroxide. If we just break this bond, how do we decide who gets the electrons? Well, they each take one. They parent trap it, if you will. Anybody watch Parent Trap growing up? Yeah. Parents get divorced and each one takes one twin.
Oh no. That's messed up.
It is a messed up movie, but it was a Disney movie when I was a kid. Really fun thing.
They find each other and switch.
They find each other and switch, yeah. Anyway, homolytic bond cleavage, usually that is going to be 2 equally strong elements on each side.
We indicate a charge on that. Yeah.
So So if we actually look at this, if we look at what happens, if we do a homolytic bond cleavage, we get oxygen. It still has its two lone pairs, it still has its H bond. If it has just one unpaired electron there, if we look at the formal charge for this one. We're gonna have this oxygen actually still owns 6 electrons, right? And it has 6 electrons on the periodic table, so it actually doesn't have a charge. It's really unstable because it has an incomplete valence, but it doesn't have a charge. And so the way we indicate that is by using just a dot to show that that is a free radical. Because we can't just say positive or negative like we normally would. And so it can be a dot product, dot if you're typing this or anything like that. You could put a dot product as a superscript, trying to make it look like that, but it's nothing you need to worry about too much. Just find a dot character that you can use, and pretty much everybody will know what you're talking about. That's the only place where we're not looking.
And light does this, right, the hydrogen dioxide.
Light does this to peroxides and most halogens. Basically, anytime you get a bond, a sigma bond, that is low enough energy that by shining the visible light on it, you can promote an electron from the HOMO to the LUMO. The LUMO looks like bond breaking. The LUMO is the anti-bond. So it only happens with sigma bonds between atoms that are low enough in energy, that are unstable enough. So that's why we don't see this with oxygen gas. Oxygen gas doesn't break down under UV light because it's got that pi bond and the sigma bond is so stable. It wouldn't really work with ozone because you got resonance in there. It'll work a little bit with ozone, which is part of why ozone is so important, is because it does absorb UV and break down and then reform itself up in the upper atmosphere. But that's the really high energy UV light.
That E side structure you were talking about before, it goes through the same process or would have the same?
Wait, so everything's gonna have some wavelength of light where it'll absorb, that'll cause it to break apart. Usually it's just high enough energy that we don't see it on the surface of the earth. But azide is one to watch out for. Azide is really, really reactive. Actually, the worst accident in a lab that I've ever seen personally was a buddy of mine in grad school who did that click reaction. He was doing studies on azide, and he'd done this reaction, you know, hundreds of times before, and he was in the fume hood. And there's a step in the reaction where you have to add the azide 1 drop at a time, slowly enough that it doesn't get away from you. And he was talking to somebody else and adding it at the same time, and he added 2 drops at the same time, and it blew up in his face, literally. So azides are really reactive for other reasons. Ozone's actually a lot more stable than azide. But so with it being that reactive, almost certainly, yeah, UV light is going to cause it to break down too. Yeah, they evacuated the whole engineering department at CU, which was University of Colorado Engineering Department, because they had 1,000 students. They evacuated the entire building, and he had 3rd-degree burns on his head and his face.
No glass in his face though?
No glass in his, he probably did have some, but that was not what caused him to take forever to come back. But he was out for a month.
Cause he didn't get shard glass in his eye. I mean,
Yeah, oh, he had his eye protection on.
That's awesome.
So his burn was like here and here around the glasses, basically.
Some time for work.
Yeah, no, it was not pleasant for anybody.
Sit on the studies.
You ever watched the video for it to be brighted?
Why would you watch that kind of video? That's stuff like that is why I get in healthcare. My wife loves to watch like pimple popping videos and like medical procedures and stuff like that. I can't handle it. I have to leave the room.
Yeah.
Important thing to notice here before we move on from the slide is that this is SP2. It behaves like it's SP2. It shouldn't, because it still does have, even the oxygen we can still does look like it still has 4 electron groups around it, so it seems like it should be sp3, but radicals that partially filled p orbital doesn't hybridize the same way because it's higher energy than the other ones. It stays unhybridized. Which means it stays planar. So in a lot of ways, and its stability of these radicals also follows carbocations. So our radicals will react. In a lot of ways, they'll react very similarly to a carbocation. They're planar. Tertiary radical is more stable than a secondary, and so on. Just like we saw with carbocations. Which we have it here. So the way we rate these is we can actually use, if you remember talking about bond dissociation energy, which is the energy in a bond. That is relative to a homolytic cleavage of that bond. So it actually is, we have to make approximations with the stability of things, but we can actually just use bond dissociation energy to rank these. So it takes 435 kilojoules per mole to split up a hydrogen off of a methyl homolytically, but only 410 kilojoules per mole to break a primary hydrogen off, 397, 381. And just for context, at about 100 kilojoules per mole is a reaction we would expect to see happen naturally at room temperature. So this is still way higher activation energy than we would normally see happening at room temperature, which is usually why we have to have some sort of initiator, some sort of catalyst to start the process. Right, so one way I can ask you about this is just like with carbocations, rank them in order of stability. But it's pretty straightforward for us at this point, right? Tertiary is most stable, then secondary, least stable is going to be your primary. And you will see, let me see. In theory, you should see some amount of rearrangement, but this is kind of like mass spec, and they're so unstable and short-lived that usually before it has a chance to rearrange, it'll react with something. So free radical reactions are a little bit less predictable than other reactions in that just based on probability, there's a chance that if you made this molecule, it would rearrange, but there's also a non-trivial probability that it's going to react before it has a chance to rearrange. So you get a mixture of products usually with these free radical reactions, just because the intermediates are so unstable.
Would it be arranged from tertiary structure?
No, if it's tertiary, then it's just gonna stay tertiary.
So those would be more predictable. Okay.
Yes, the problem is the way that we actually make these carbon radicals is basically by having an initiator molecule like this, and then it goes in and it'll just randomly, if it bumps into this molecule before it's a radical, it'll just, whatever hydrogen it bumps into, it just steals it. And it leaves a radical wherever that is, because of how unstable this is. And so you actually wind up with a mixture. If we actually put this molecule in the presence of hydrogen peroxide and started this process, you get a mixture of all three of these. And it's not just based on stability, it's also based on how many possible molecules or hydrogens could it bump into. If there's more hydrogens that give you the same product, then there's a higher probability that that happens. So we actually wind up with having to take in statistics to some extent. We're not going to do a whole lot of statistics with it, but just in terms of raw probability. Like for instance, if we were going to make, if we looked at pentane, if we pulled a hydrogen off at random from pentane, pentane is C5H12, right? So there's a total of 12 hydrogens. 6 of the hydrogens will give you the primary radical. So that's a 50-50 shot at making the less stable one versus there's 4 hydrogens that will give you the secondary with it on carbon 1, carbon 2, or carbon 4. Those would both give you the same radical, right? That's a 1 in 3 chance, but then you're making something more stable. And there's only a 2 out 2 out of 12 chance of it pulling hydrogen off from the middle, right? So you wind up with the statistics and the probability playing a role as well, because whatever it bumps into first, it's gonna grab. And there's a better chance that it runs into a methyl than it is one of these other ones, just because there's a total of 6 hydrogens to give you that. Even though some percentage of the time then it's gonna turn around and rearrange. But really, because it's so unstable, this whole process is so unstable, you just get a mess of products. And we can usually rank them based on, if we can control the reaction conditions just right, we can get it to favor one of those, but you're gonna get a little bit of everything. In this case, even more than the other cases we've talked about so far.
So you mentioned the ring structure, that they don't pull the hydrogen off the ring structure so much.
What do you mean?
The, like this molecule will come over to, we got you read the, yeah, that, like.
Yeah.
Pull hydrogen off of the.
Oh, yeah, no, it'll do that
So
too.
that's it.
Yeah, just out of these 3, we were just ranking them.
Yeah.
But you'll also get somewhere, you'll hide this hydrogen off, or one of these 2 hydrogens gives you the same, one of these 4 hydrogens.
Yeah.
One of those 4 hydrogens, one of those 2 hydrogens, you're gonna get all of those. And in some cases, you can't even predict necessarily what the major product is going to be. There's competing variables. One thing we can say though, is because resonance is even more important in radical stabilization than with carbocations. If we have the possibility of giving our radical resonance, that's gonna happen. That's way more stable than any other radical we can have. So that is the case where we can pretty much predict if it's gonna give you resonance. If we have that allylic position, has a hydrogen that can be pulled off, it will. And just a reminder, now that we're talking about these homolytic versus heterolytic bond cleavage, remember to look at the barbs on your arrows when we're drawing these mechanisms. If you're showing both electrons, you draw both barbs on the arrow, on this arrow. If you're showing one electron goes one way and one goes the other, notice that these arrows are only single barbed. Right, and that's how we indicate that one electron goes one direction, one goes the other. And we wanted to draw the resonance structure for this. We would show something pretty. We would use something fairly similar. We'd say this electron is going to move over, and one of these electrons moves over too. The other one's going to go the other way. So for this particular molecule, our resonance structure would just look like same thing flipped. So similar to other resonance structures in that it kind of has the net result of a charge or a radical kind of alternating carbons when it moves around like that. We just have to be careful about drawing those arrows that we show it. We don't give too many electrons to any one carbon.
Yeah, we're not.
Right, we're actually breaking a pi bond and making another one.
Which makes sense with being kind of like SP2, like.
Ish, yeah.
So,
Exactly. So it works the same way as a positive charge being moved around. Like I said before, there's a lot of similarities between how carbocations and how radicals behave. Everything's just more extreme with the radicals because there's so much less stable. So, and this is just showing you the map. So this is continuing that same figure from before. When we were talking about carbocations, we put allylic, we put resonance stabilized carbocations in secondary. We're roughly as stable as each other, right? We're actually even more stable. If you look at going all the way from a methyl bond association energy all the way to benzylic, meaning can resonate with the benzene ring, are almost 100 kilojoules per mole different, or 80 kilojoules per mole different. Which is an even more extreme energy differences than with carbocations. Right, so. That winds, this order of stability is gonna wind up playing a pretty big role in determining what products we make. Because when we, the way that these reactions are gonna work is we're basically gonna pull a hydrogen off of an existing molecule, an existing stable molecule. To make a radical, and then that radical goes and reacts with something else. So knowing which hydrogen to pull off, the probability and how many of them winds up playing a role in it, but the other aspect, all of the things being equal, is you just look at which one's more stable, and resonance matters a lot in this case. So one of the ways I can ask you a question about this is, okay, well, which is the weakest carbon hydrogen bond in the following compound? So in other words, which hydrogen are you most likely to pull off? Or is easiest to pull off in a heterolytic or homolytic bond cleavage? We've got a tertiary. We've got secondary, but with resonance. So this one is going to be the easiest one to pull off. So the most stable radical we could make from this molecule would look like that. All right, let's take our break there. So to this point, it looks a little bit different, a little bit weird, but no new rules really. So it's not too bad yet. The way we draw these mechanisms winds up getting tricky, and that's what we're going to spend the second half of the lecture on. So let's come back at 5 after.
Wait, is he doing anything fun this weekend? Did anyone? No. I never heard. No. Well, I did actually, I did one fun thing, it was all work, but I got to do a big bonfire, because there was a bunch of stuff like wood that I found that you could be burning, we had a bunch of yard waste, so I just. Had a bonfire yesterday for 6 hours. That was my plan. Made a bar maniac and tried to help me. It wasn't anything that had like varnish or that shouldn't have been burned. It was really, it was like, so.
Better off being burned than just put in the landfill. My mind, like oranges and shit in the one of those.
Yeah, it's just getting broken down into mostly carbon dioxide and water. It's like a couple.
The eye roll.
Yeah, mostly. Also like an expired truckload of stuff, which would be like 40 or 50 bucks. So it's like. That we have to take, I don't have a trash service where I live up in Pioneer,
Yeah.
so it's literally everything we had. Built this little box, wooden big box thing where you can put like, I don't know, a couple months worth of trash, and then we burn all of the like, stinky stuff. Or like freeze it, throw it away. Yeah, it's yeah, right.
Burn the trash, it goes up, it turns into stars.
Pretty much. Well, and we also, because we have a septic system that we can't like flush toilet paper or anything. So all of that has to be like collected into the trash can and thrown away. So bidets are great.
Rest of the world doesn't use toilet paper.
Well, it's like you only have to use like a couple squares of it to dry up rather than. I mean, 1 through 10, depending on the severity. LDH.
That high pressure one that they use to like hold the fire back if it's rushing out of the door.
That's the 2-inch, 2.5, that's the 2.5.
Yeah, exactly.
That one's gnarly, dude. It's like you have to wrestle it. I was on the fire department for a while, like, we all in all, like 6 or 7 years. The 2.5 is like you were putting all of your, not like 200 pounds.
Yeah.
And like 230, 240 in gear, right? And it's like all of your weight on it just to keep it controlled.
Yeah, and someone else is holding the hose.
Oh, yeah, someone else is backing you up. It's a 2-person job, like, especially when the engineer like puts the pressure up near like 100, 120 PSI. It's like, that thing gets away from you. It's like,
Yeah, it's totally scary.
yeah, yeah. And then you have to like run back to where you can like get on the hose if that happens, and then like crawl up it. And, like, as it's like trying to smack you in the head.
Like it's anaconda or something.
Yeah, it's a fun drill to do. It's always fun, like, watching someone who has never done that before. It's just like so like nerve-wracking watching people go through that the first time. It's hilarious.
And I was in like second grade, the first grade, and the fire department came.
Yeah.
So they're like, bullets get sprayed back or someone like ready to catch us.
Exactly. Yeah. Well, it's like one of my favorite things to do. Yeah, like the elementary school. So then we have a big tower truck. It had like this, I don't remember how tall it was, but it was like almost 100 feet. This insane ladder with a bucket on the end of it.
Oh, yeah.
And so we did the egg drop contest.
From the top.
Yeah, so you did take that thing up to like 40 feet or whatever, and then like increment it, the ones that survive.
No wonder fucking eggs are so expensive now.
That was fun. I kind of miss it. I'm good. It's still part of your body. Yeah.
Started watching the new podcast. It's just go around the world. Take travel.
Oh,
Yeah.
Oh, yeah.
You're tripping.
That's not a trip. That's cool. I like watching some of the, I think it's like Relaxing Walker is his name. But he does a bunch of just walks through different different cities and stuff, and he just carries his like camera and stabilizer. So you get to see like everything, see all the daily lives.
It's not going anywhere, he's gonna get robbed, it's just film himself get robbed. Oh, they have my camera, now they're filming themselves with his camera.
No, our latest one I watched, there's a walkthrough of Somalia.
Oh, shit.
There was like a decomposing dolphin, like on the street somewhere randomly at one point. I was like,
Dolphin that blew up.
yeah, no, literally, it's like the top half of a dolphin rotting. It's like, what? And then actually you should totally find it. It was highly entertaining because he finds like the pirate king of Somalia, like dude's all like dressed up in like a collared shirt and everything, has a nice watch and has a gold pimp cane and is like, and like nice glasses.
Broken Bankrupt? Is that his name? Like on YouTube?
Oh, I'm not sure.
No,
The dude
the dude that does all
There's Relaxing Walker, I know.
the, yeah.
He has good ones, but yeah, I remember he did the Somalia ones. It might have been.
Are pirates allowed Instagram accounts, like, are at that point, they wouldn't need it, they'd be breaking so many laws, they can make money off. Media, but they're not.
But it was hilarious because like the Pirate King, and I just call him that because they have a good king. So he just automatically gets that title. But it was hilarious because he was talking like about moral philosophy and basically like how it's like on Somalians to make their country better, and so he's like kind of calling back all the Somalians who have left the country, like come back to your homeland, you know?
See, is it this guy? And the guy.
No, it wasn't that guy. Yeah, it wasn't that guy. It was.
Sounds like more of a touristy thing to do, to go walk around.
He was actually. He was followed around by like an armed guard the entire time. It was on YouTube. There was like this dude who filmed a trip to Somalia and did like kind of a walking tour of Somalia. And it was crazy. There was like a rotting half dolphin in the middle of the street at one point.
He's got security guards and stuff. Yes.
There's a lot of weird YouTubers out there that do stuff like that.
Yeah.
These days, like it's, you know, my kids, I can't handle a lot of like the travel YouTubers because they're like that.
Pretentious.
They're pretentious or they're gimmicky. My kids like Ryan Trakings. You guys know who that is? He drives me nuts. I can't stand it. He is kind of funny sometimes, but it's just obnoxious. But anyway, YouTubers. Good. All right, let's talk about mechanisms. The main thing with mechanism, so it's going to be different than the mechanism that we've seen in the past, and they're different steps. But there is a process to writing free radical mechanisms that is, if you make sure you have the right steps, the right sections of the mechanism, you should be able to get the right mechanism every time. So homolytic cleavage, addition to a pi bond, kind of looks like the resonance structure we practiced a second ago, right? We break a pi bond to make a new sigma bond. In this case, hydrogen abstraction is what we've been talking about. Abstraction just means pull something off. So a hydrogen abstraction means you're pulling a hydrogen away from a carbon. You can actually do the same thing with a halogen, especially a halogen that's got a single bond to another halogen. So we see this a lot with Cl2 and Br2. And then we can also even have leaving group leaves, sort of elimination reaction, where we wind up with basically undoing addition to a pi bond. And then last but not least is you can have coupling. And coupling in this case just means that two free radicals run into each other to remake the same bond. So two of these are actually opposites of the other side. So our elimination and our addition are opposites, just like we've seen before with other elimination and addition. And the homolytic cleavage and the coupling are just opposites. Right? Homolytic cleavage, a sigma bond turns into two radicals. Coupling, two radicals turn into a sigma bond. The other thing to keep in mind with these is that they're generally going to fit into one of three categories. if you have a mechanism step where you get more radicals out than you started with. So for this first one, we started with 0 radicals, we made 2. The other word for that type of mechanistic step is it's an initiation step. And then if you start with more radicals and you use some up, like in this coupling step, we call that termination. So initiation starts it up, termination ends this process. But you'll notice that all of these other ones, you start and end with the same number of radicals. So while you do have a net reaction happening, the overall process, we still create something really reactive on the other side. Because for each of these, you have an odd number of electrons. If you have an odd number of electrons, you can't have everything be paired up, right? And so with an odd number of electrons, you're gonna start and end with the same number of radicals, just what the radical is changes. And so they call this propagation. Propagation just means to keep something going, right? Like when you propagate a plant, you're taking a cutting of it and you're replanting the cutting, continue that plant growing somewhere else, right? Propagation in terms of chemical reaction means we still made something that's almost as reactive as what we started with. And so this process just continues on, which is one of the reasons why the CFCs in the upper atmosphere reacting with the ozone, that's a free radical reaction and it keeps going basically. Because all of the reaction steps that could happen up there that are favored by statistics, by probability, were propagation steps. You had a small number of initiation reactions happening, and then you had a whole bunch of propagation steps that just keeps things going. And these are all close enough to the same amount of energy before and after that they can keep going indefinitely. Until you wind up with enough free radicals where it becomes statistically probable that you start seeing termination steps. So when you have a termination step, that's actually going to be the end of the reaction. But until then, you just go until everything reacts, basically. And it will just continue on because it's so unstable. All of these radicals are so unstable.
And is this like fairly exhaustive as far as like how radicals behave?
For the most part, we're going to look at a couple different versions where basically the initiation step and the termination step always look the same,
Right.
more or less, right? We'll look at very different variations of these 4 middle ones that give us different net results. But the most important one is actually going to be this one. Because if you start with a halogen and you go through a free radical reaction, you can actually take a alkane and you can turn it into a free radical, which then reacts with more halogen to basically put a halogen on your alkane. So this is how you make things like bromobenzene in the first place. If you start with bromobenzene's wrong, bromobutane. You start with just butane and bromine. If you shine light on the bromine, we get an initiation. And then we do a hydrogen abstraction from the butane. And then the butane radical turns around and reacts with another bromine, which then turns around and reacts and abstracts another hydrogen, and it just continues on. But what you get as a net result is you turn butane, something with no functional groups, no reactions we can really do with it. But all of a sudden, this gives us a way to add halogen to it. And once we have a halogen, that opens up all the rest of our reactions, right? As soon as we have a good leaving group on it, now we can do elimination, we can do substitution. And then once we do elimination, that opens up all of our alkenes. Right, so this is a good first step. If you're starting from an alkane, your first step almost always in the synthesis problem, if you're starting from an alkane, is put a handle on it. We're going to say put a handle on it so that you have something you can grab onto and manipulate it around with. And number one way to do that is by adding bromine.
And then is there, with that, any way to control kind of which you get, right? Cause you get a bunch of products.
You're gonna get a bunch of products. So we can predict which one's gonna be favored. You're really gonna get a mixture of a bunch of them. But we're usually gonna have a major product and then large amounts of the other ones.
You have to do like a fractional distillation.
So you have to do something to purify it. Yeah, exactly. But then, once you get to bromobutane, now we have something we can work with.
Yeah.
So when we see the extractions happening in reverse,
Yeah. Sorry, say that again?
the extraction. How would you extract it? Would we see those happening in reverse, much like we have addition?
It's more likely it happens in sequence. This one happens and then this one happens and then this one happens and then this one happens. That's why they call it propagation.
I see.
Because the product from the hydrogen abstraction is a carbon radical, which then can go into a halogen abstraction, which makes another halogen radical, which can then jump up over here. So it's not so much that it's going back and forth, it's going repeatedly in sequence.
Right, so it won't happen like in reverse, but opposite.
Not generally. Now, even if these are close to the same energy before and after, we are generally still progressing towards a more stable state, and so the odds that it goes backwards are pretty low. Especially considering if you only have a small number of initiation steps. That small number of initiation step means you have a lot more of the normal alkane and the halogen than you do radicals at any one given point. So the odds that two radicals run into each other are pretty low, at least at first. Let me. There we go. And just another terminology note, those single barbed arrows that we draw, sometimes you'll see it, see them called fishhook arrows. That just means that's just reminding you to make sure that you're showing the right number of electrons moving with your arrows. So here's an example for one of these radical reactions. It works better when we have the bonds that are breaking drawn out. If we have a tertiary radical here, and it runs into a bromine, you're gonna wind up with a homolytic cleavage. And we're gonna end up adding a bromine where the radical was and making another bromine radical. Right, so that's a halogen abstraction, which then this can turn around and react with something else. And are there other things it could run into? Could this run into another molecule of the alkane? Yeah. But in general, we're going to show the steps that lead to where the major product, what the major product is. We're not going to show all the possible propagation steps because there's going to be a ton of them. Right?
Too much.
That would be way too much, because even this could then, if this radical then did a hydrogen abstraction here, you could actually wind up dibrominating something, right? But the probability is that this is not going to run into another molecule that looks like this, because there's, at least at first, there's a larger probability it's going to run into unreacted reactant than it is going to run into a product that's already been made. So at the end, when you're sort of scraping the bottom of the barrel, when there's very little of your unreacted reactant left, then you start making some of these more weird combinations where they're being smaller amounts, but based on probability, we can say that most of our product is going to look like this, and we're going to get, single digit yields or less than single digit yields of all the other possibilities.
And is that something you can kind of like modulate with time?
A little bit, if you control your concentrations.
Yeah.
The lower your concentrations are of your reactants, the higher the likelihood that your intermediate is going to bump into something you don't want it to.
What is the catalyst for these reactions?
These aren't, so not really, mostly because these the reactant or the catalyst in this case is gonna be the initiator, whatever starts the process. And once you start it, it kind of just trucks along on its own until it runs out of steam. So you can't really, you can change how fast it goes by shining less light on it at the beginning. And let it go longer. That way, but it's not really gonna change where you end up for the most part, because the main thing is what are your probabilities? And that's not changed by how much initiator you have or how much initiation step you have usually. Does this work? Doesn't, there we go. Alright, so this is just. Showing those three categories that I already talked about, initiation, propagation, termination. And when you're writing out free radical mechanism, you're going to write all three of those categories. There's always a termination step. Or sorry, there's always an initiation step. There's always propagation steps, and you always show a termination step. And we're not gonna do it exhaustively, like we talked about. We're gonna show the propagation steps that lead to your most common reactant. And we're gonna show the termination step that leads to your major product as well.
So the major products usually just the termination.
Right, so if we look at that molecule from. Was it just methyl cyclohexane? So we look at this. Plus a bromine radical. That's a termination step that gives us our major product. So that's the termination step we show. There could be a termination step that looks like this running into another molecule that looks just like this, and you get some weird fused ring structure, right? Or your termination step could look like a bromine running into another bromine. Or a bromine running into some weird free radical that already has been brominated once. But the one that we're going to show is the one that leads to our major product. And we do the same thing with our propagation steps. Our propagation steps, if you for any free radical mechanism, when you write the propagation steps, you want to be able, it's always going to be more than one. And we're going to write them so that when you add the propagation steps up, all your radicals cancel out from both sides and you get the overall net reaction. Basically, yeah. So for instance, let's start with the simplest one, methane going through a free radical mechanism. And one of the ways that it's going to be going through a free radical mechanism is one, if you start from an alkane, because alkanes don't have any reactions, right? They don't have any functional groups to speak of. The other big clue is if you see light as a catalyst. Right, so in this case, shining light on methane doesn't change anything about it. It's usually going to be the halogen or the peroxide that when you shine light on it goes through an initiation. And the way we write these, we would just label it. And we're not going to write them in sort of in sequence like we do with other mechanisms where it shows like a linear pathway. We're just going to write a bunch of steps. Like these can all happen. One's an initiation. Usually there's 2 propagation steps, sometimes 3 propagation steps, and then you show 1 termination step. But it's not like one leads into the other the same way that we would normally write our mechanisms. So our initiation step in this case will just look like that. And we make 2 radicals.
Pretty consistent with the reaction showing over the arrow, or maybe instead of that really consistent.
For the most part, yeah. You're not going to see an initiation step that involves an alkene. It's almost always a halogen or a peroxide. There are a couple of other cases in there, but you kind of have to use the context clues a little bit. The termination step that we're gonna draw sometimes, and it can also be helpful to start at the beginning and the end. Just while we're thinking about the initiation step, think about termination step. I take that back, I don't wanna do it that way. Propagation steps are what happen next, and it's basically take the free radicals that you make in the initiation step. And then see what that it has that can react to it, so. Propagation. It's gonna look like. Not both of them. Chlorine radical. Plus methane. It's gonna do a hydrogen abstraction. Just basically that the halogen radical just pulls a hydrogen off. And we're gonna make HCl. Yes. And. Methyl radical. And we know that this is a propagation step because we end with the same number of radicals we started with. And remember that in our propagation steps, we want to show our primary product, methylene chloride or methyl chloride. So what's gonna be a propagation step that this could react with? It's gonna keep this whole thing going. Cl2. So if we have our methyl radical plus another Cl2. We're gonna make our chloromethane plus another chlorine radical. And the process could start again, right? This is what I mean about them happening in sequence rather than back and forth. It's not an equilibrium process, it's just that it keeps going. And our net result, if we added these two reactions together, anything that's both a reactant and a product cancels out, right? So if we added these two things together, we got chlorine radical and as a reactant and as a product. So if we added these together, they would cancel out. And we have methyl radical as a product and a reactant. So they're going to cancel out. So our net result of adding these two things together is methane plus chlorine Cl2 gives you methyl chloride and HCl. So that's how we know that we wrote enough propagation steps. Are there other propagation steps we could draw? Absolutely. We don't need to though, because these ones add up to give us our net reaction.
Do we need to include all of these even? Because you can just take another chlorine radical and just terminate this right there, right?
So the initiation step, you're never going to be able to add your initiation steps to a propagation step to get to the net reaction, because if you do that, you're going to wind up with a net increase in radicals.
Right. There's
So-
two here and then there's one in the first. Right.
You can think of that as adding on twice, right?
That's
The other thing that we see is when we look at the termination step, that's going to make it all add up too. Because at this point, we have initiation and propagation, we don't have the end of the reaction yet. And so the termination step can be any two radicals that you drew in the propagation could run into each other and do a termination. However, we usually pick the ones that will give us our major product.
You would have known some ethane.
You would wind up with some ethane, you would wind up with some leftover chlorine too, especially if you're not continuously shining light on it. If you happen to remake chlorine gas and you're not shining more light on it, you still get that chlorine gas will still be stuck around a little bit too, right? But the one that we always show is the one that is our major product. So we want to show the two radicals that give us the chloromethane. So our termination step that we're going to draw is going to be methyl or a chlorine radical plus a methyl radical gives us CH3Cl. I'm not gonna be as picky on the termination. I want you to show the one that's gonna be give you the major product, but the main thing, the trickiest part is how many propagation steps do I need to show? It's gonna be, you show them so that it adds up to your net reaction.
I kind of, with what Zeke is saying though, I kind of see that, because if you have the initiation radical, you make two of the chlorine radicals, and then you use one of them in the hydrogen abstraction, and then the other one of them in the termination. Then that doesn't count for all of them, right?
It does, I mean, in theory,
I don't think it'll be that clean during your month.
right.
Yeah.
I don't know.
So remember, we're just looking, yeah, we're taking a very specific look at certain molecules.
And you said it's happening twice, so that means that.
Yeah.
Both of those chlorines
Right.
are being used in this process to create,
Yeah.
Right. Right, so these are more just talking about the steps there, just drawing it more cleanly than I did. Right, and I didn't get a chance to use the restroom on our break, so I'm gonna go do that while you try and draw your own mechanism here.
So geometry works out for that, but. The other end, well, I don't think. Right, yeah. I think there would be excess. Okay. Throughout, there would be excess methyl radicals that would terminate equally, so you'd be left with a radical. And something like that. Draw out, yeah, draw out. I'm doing well. No, I think. Yeah, I totally see what you're saying now.
So actually, this is the process by which they make all of the chlorinated methyl chlorides. You got chloromethyl methyl chloride. Methylene chloride is the common name for dichloromethane that we use as a solvent. Although apparently not anymore, it's been. I think it's on the list of things we're not supposed to use anymore. Because there are other options that are less problematic. If you chlorinate dichloromethane, you get trichloromethane, which is better known as chloroform. And if you chlorinate that, you get carbon tetrachloride. So you actually, in each of these, it's gonna have its own set of, it's the same mechanism with a different starting point from each of them. The net result for all of them is you take a hydrogen off and you replace it with a halogen, and then you make the halogenated or the acid as a side as the other product,
So
right?
basically, you're doing it twice.
Basically, you're gonna be
With the termination product from the first.
correct for the termination product for the
then you
first,
add more
exactly,
diatomic chlorine, and then you go through the whole
right? So
initiation propagation to get.
exactly, and your initiation is gonna look the same. Because your initiation step is still just gonna be chlorine plus chlorine. In the presence of light. You're gonna make two chlorine radicals. It's the other way to think about the balancing of this too, is that one of your chlorine radicals. Goes towards creating HCl, doing that hydrogen abstraction, and the other one, like you said, gets used up in the termination step. To make the product as well. It does all balance out if you're careful about adding all of the reactions together, if you write them properly. But again, that's not usually what organic chemists are as concerned about, making sure it's totally balanced, as long as we can predict what the organic product is going to be.
And so like with each of those steps, basically, that could be a propagation or a termination step that results in that, whether it reacts with a Cl2 or with a Cl radical.
Exactly.
Okay. Okay, that makes sense.
And our
He's got an initiation step.
right,
Initiation step.
if we're, the way we're drawing it here, yeah. Our propagation steps here, again, there's gonna be two of them. Chlorine radical. This case, we're starting with methyl chloride instead of just methane, but it's still gonna do the same thing. It's gonna pull a hydrogen off. And then we've got H2Cl still there. So that gives us, then we get HCl, so one of our products. Plus. CH2Cl radical. Which then that's gonna react with another chlorine molecule, keep the whole party going.
Like, carrots, or you just include radical. Like very good events such as radical. Just reacting with it.
Right here,
Yeah, here.
so that wouldn't be a propagation step then. That would be, if a Cl radical reacts with another radical, that's a termination. So Cl. H2C radical plus chlorine radical. To give us our dichloromethane again. So if you're drawing these right, you should show your final product two different times. Once is a propagation product and once is a termination product. Because, and we're not gonna go down the rabbit hole and draw all possible termination steps because. It doesn't matter, there's too many of them. Right. And there are other propagation steps as well, but if they're not leading to the product we wanna show. Like, just anytime we're drawing a mechanism, there's almost an unlimited number of possible bonds we can show breaking or transferring or something like that, right? we only show the ones that go the way we wanna go.
So like on a test for the formation, the final product showed both the propagation and termination steps. But maybe.
Yes.
Okay.
It would, you know, we wanna show the steps we care about. If you're trying to give me directions from here to Paris. I don't need you to tell me about how you know, how Apache comes off of 50 in Myers, right? That's, yes, that's true, it's also not relevant. Give the steps that go where you wanna go. All right. When we're looking at the thermodynamics of these, talking about enthalpy versus entropy. Do we need to really worry about entropy? We have two distinct molecules, we still have two distinct molecules, so. There's a small change in entropy. Because there always is a little bit, because this molecule hasn't inherently has a little bit different entropy than methane does. But it's not gonna be very large. Pretty insignificant, so if entropy doesn't dramatically favor one side or the other. That means that the enthalpy really is going to be driving things, it's actually the bonds themselves that are gonna drive our equilibrium in this case. So if we look at bonds broken and bonds being formed. A carbon hydrogen sigma bond and a carbon halogen sigma bond are roughly the same energy. And a hydrogen halogen sigma bond. It's not super stable, but this one is noticeably less stable than any of the other bonds on here. These halogen single bonds or these peroxide single bonds are so high energy that that's going to drive our equilibrium towards the products. We actually put numbers to it. These, if we look at these different reactions, just with the different halogens. Fluorine F2 is so unstable that our delta H is negative 430 kilojoules per mole. In other words, you don't even need to catalyze this one. This one is so downhill in energy that this will happen regardless of if you catalyze it. And usually explosively so. So basically, we don't use fluorine in these reactions because you shine light on fluorine, it blows up effectively. It happens so quickly and it's so exothermic. Chlorine and bromine are both exothermic, but less so. And then iodine is actually uphill in energy. Iodine single bond is actually stable enough. And these bonds are weak enough that you actually have to go uphill in energy to use iodine. So like we saw before, we don't see fluorine and iodine used a whole lot in these mechanisms. Which is fine because chlorine and bromine are both adequate leaving groups. If we wanted to then use this in a synthesis process, there's no reason why we need to make methyl iodide instead of bromomethane. It's more convenient in some cases, basically just because it's a liquid at room temperature. But other than that, from a reactive point of view, this works well enough. And the difference between chlorine and bromine, we're actually going to spend some time on that because chlorine is the one, it's so reactive that it's just going to react with whatever it bumps into first, regardless of what's more stable. So chlorine is going to be, we're going to halogenate, or we're going to chlorinate alkanes based just on statistics. We're looking at what our mixture of products is going to be. Chlorine radicals are just so reactive that you don't see any specificity. It's just how many options are there. We're looking at butane being chlorinated. Butane's got a total of 10 hydrogens, right? You got CH3, CH2, CH2, CH3. So it's a convenient one because 10 hydrogens means we can do the percentages easily in our head. If you chlorinate this, we're gonna get 60% of the 1-chlorobutane and 40% of the 2-chlorobutane. Almost on the nose. But because bromine is not as downhill in energy, it can be more selective. With bromine, when we brominate alkanes, we favor the more stable radical. So we'll actually make more of the 2-bromobutane than the 1-bromobutane because the two, putting the radical on the second carbon is more stable. Right, so basically by picking and choosing which of these we use, we can put the halogen, we can change what the major product is in some cases. Generally speaking, bromine is more favored just because it's more selective. Reacts a little slower, it's easier to work with. Bromine's a liquid at room temperature instead of a gas, so that's helpful as well. And we can be more careful and predictable about where we're going to add it. Using chlorine is great when you want to make with one of the less stable halides. And you don't care if it's got great yield, you just need to make some of it. Then you wind up using chlorine.
So if you wanted to make like something where a primary radical, you use chlorine, was if there was like a tertiary radical, that would be unlikely, but then you use bromine to get more of that.
Right,
That kind of thing.
because almost always you're gonna have more hydrogens on primary carbons than on secondary or tertiary, right? Because fewer of the bonds are taken up with carbon-carbon bonds. And we can, again, we can predict pretty easily what the mixture is going to be. So if we looked at methyl cyclohexane. There's 1, 2, 3, 4, 5 different carbons that have hydrogens we can pull, that we can add a chlorine to. There's a total of, let's see, there's 6, 7, so there's 14 hydrogens total. Only one of those 14 gives you the tertiary product, right? So that's a 1 in 14 chance. And we can expect the ratio of products to be whatever that percentage is. About what, 7% maybe? Yeah. Versus there's 4 hydrogens that give you the product where you put the chlorine on the secondary carbon. And there's 4 here that get put it 1 carbon away. There's only 2 there, so you get a 1/7 that, and there's 3 out of the 14 where you put the chlorine on the radical or on the methyl group. Right, and so if we actually want those percentages, you just look at how many hydrogens can give me that product, divide by the total number of hydrogens that could be pulled off. With the bromines, it gets more specific. If we brominated this, we're going to make the tertiary product because bromine is more picky about which hydrogen it pulls off. It's not reactive enough as a radical to just pull off anything at random. It's going to pull off the easiest hydrogen to pull off. You'll still get some of the other product as usual, but all right, so this is the thermodynamics of the propagation steps. So just what we were talking about, having the chlorine radical pull off a hydrogen to make HCl, the alkane radical, it's still downhill in energy, but it's actually uphill in energy for the bromine. So that's actually going to slow things down. The net reaction in the case of the bromine is -50, but both of these steps were downhill in energy with chlorine. And that gives you a more favorable overall reaction. So the chlorine reacts more completely and more randomly. Bromine is more selective, which also means slower. Right, so here's just the potential energy surfaces of those two reactions, right? And so this is just walking through the regioselectivity of the different halogens. In this case, so for propane, we would expect 75-25 of the 1-chloro versus the 2-chloro. And that's close to what we get. It's not 75-25, but definitely. The stability of that radical does wind up affecting it. Let's see. So this is looking at how chlorination versus bromination. And this goes back to what was called, we talked about a little bit last quarter, the Hammond postulate. We didn't really talk about why it was important as much. And it's still not super important, but there's this idea that whether either the reactant or the intermediate is usually going to be closer in energy to the transition state. Whichever one is closer in energy to the transition state is going to tell you more about what that transition state looks like. What's the physical spatial orientation, as well as what are the orbitals doing. So which one of these is going to have more? First off, which one is the radical, the reactants or the intermediates? To the intermediates, we had to make the less stable radicals. So if we're going uphill in energy to get to the radical, in the case of the bromine, then our transition state looks more like all this is saying. In this case, because the intermediates are downhill in energy from that first abstraction process from the chlorine, your reactants look more like the transition state than the intermediate does. Has small impacts as far as the stereochemistry. What that basically means is in the chlorination process, the carbon hydrogen bond is a lot stronger still in the transition state because it has less radical character on the carbon because it's closer in energy to the reactant side. Versus with the bromine, the intermediates are closer in energy to the transition state. So that changes how big that bond is in between. Basically, how broken is that sigma bond and how formed is the new bond is going to be based on energy of the transition state versus the intermediates. Again, let me fix that figure so we can see it. Basically, we still don't see like that pure statistical mixture with chlorine because it still is going to be easier to pull off a secondary compared to a primary, but it's a lot more random. You get double-digit yields of almost everything in the case of chlorine. Versus with bromine, we get almost 100% yield on the most favored product, one where the hydrogen's easiest to pull off. Especially in the case of tertiary versus primary. So basically that just allows us to say when you're dealing with chlorine, draw all your possible products. It's still, this textbook is saying, you're going to get, sometimes it's hard to predict because this is the more stable one, but there's 9 hydrogens out of the 10 that give this product. So it's still not a 90-10 ratio, but you are going to see your major product. But basically with chlorination, I'll either tell you on a test, like what is the statistical mixture you would expect, ignoring stability. And then I expect you to be able to look at it and say, okay, 90-10 or 60-40 or whatever the ratio of hydrogens is. And you can do it as a fraction too, since this is not a math heavy class. I don't expect you on a test necessarily to have remembered your calculator for this class. So if you wrote 1 out of 14, that's fine. All right, last slide. So what is the major product if we brominate this molecule? So remember, one of the tricks is, and we all know how to count to 4 but not 5 by this point, right? So you're not just gonna stick a bromine on whatever carbon is the most substitute, because you still gotta have a hydrogen you can pull off. Right, so in this case, our quaternary carbon doesn't have a hydrogen, but our tertiary carbon does. So, and because it's bromine, we're gonna predominantly make just that product. And if we chlorinated it instead, we'd get some mixture of all possible products. There's 9 hydrogens that'll all give you the same product, so that's actually probably gonna be the major product in this case. And then there's another 6 out of, this is a total of what? Total of 8, so total of 18 hydrogens. Half of those hydrogens give you the same product, and then another 6 of them. So another third of the hydrogens give you the other primary product, and then you have 1 that gives you the most stable product, and 2 that give you a secondary one. Those will still be present in significant amounts because they're more stable. But probably it's gonna be this product if we chlorinated it.
Whereas bromine will like heavily favor.
Very heavily favored.
So that, yeah, I can see that's like super useful in synthesis, like.
Right. If you're starting from this molecule and you need to get some of the primary halogen,
Yeah.
then you can't be as picky about your yields, right? Getting 50% yield might be okay if it puts a chlorine on a primary carbon. Although maybe doing this and then an elimination reaction put together might give you a better overall yield. You did the Hoffman product for an elimination instead of one, but it's a little bit of a moving target, right? So organic synthesis has a lot of, well, this should work, but I don't know what my yields are gonna be, let's just run it. And see what we get, which of these is gonna give us a better yield, so there's a lot of guess and check, kind of. You have to know your mechanisms and your steps and why they work to even know what's a possible way to do it, but then once you have 2 possibilities, you just try them both and see what gets you the better yield. Also makes organic synthesis really, really hard to replicate because, like I said, where you in organic synthesis papers, you actually have to write in your methods, where did you get that bottle of reactant? Did you order it from Sigma Aldrich or did you order it from Flynn Scientific? Because there's going to be different impurities, and that can actually make it harder to determine or to replicate results.
Right, did you produce it yourself?
Sometimes it's down to the batch number. This batch from 2023 from Sigma gives me this result, but the batch from 2024 doesn't. It's incredibly frustrating as a researcher to read some paper that does exactly what you want it to do, and then you can't make it happen. All right, that's the end of lecture. 1 o'clock, we're 5 minutes late here, so we can start lab 5 minutes late, give you enough time to go get food or whatever you're gonna go do. And then we'll do the hydration of norbornene, which does smell pretty bad. I will warn you. So we're gonna be using the fume hoods. Norbornene has sort of a weird. Mariella really doesn't like it. It doesn't bother me as much, but she's like, oh, this is the one with the stinky stuff.
Okay, well, thank you
So-
for the.
Just a heads up. And Zeke, did that, am I supposed to email stupid myself, or are you supposed to submit my recommendation.
I was supposed to submit it to
Okay,
the application, but.
I'll send it to you later today then.
Okay, perfect, yeah, and then I'll get that application through. I think it ends 29th. on Monday.
But if you're planning on submitting it, today's the 28th.
Oh, it's. Okay. Perfect.
But I do have a deadline today, so if you'd be okay waiting to get it until tomorrow morning,
Yeah. that's fine.
if that'd be okay.
Cause they already have my resume and I talked to them already, so.
Okay.
I mean, they have all my information, they just need the actual.
The full, yeah.
Guys.
Yeah,
Thank you for that, John, appreciate that.
yeah, no problem.